I will be teaching you probability from the book right here, Introduction to Probability. I will start with set theory, and then I will teach you all the things that you can see in the graph. Let's start learning set theory first. Alright, so here is the presentation on set theory. I will link everything so you can have access to the PDF and the presentation. In this PDF, we are going to cover sets and elements, set operations, algebra of sets, and the Venn diagrams. And of course, I'm going to do some exercises too. So let's start with the definition of set. So right here you can see that a set is a collection of objects inside braces. Here are two examples, set A and B, which I'm going to work for the rest of the symbols. So each of them, A and B, are finite. Of course, if it's infinite, you're going to add 3 dots at the end of the set. The intersection of a set are objects that belong to set A and to set B. So now and here is important. For example, 9 and 14 here. Union are objects that belong to set A or to set B. Again, or here is important. It could belong to any of them, A or B, but the intersection is just anything that belongs to both of them. The union, you can see the example right here as well. Now the next thing we're going to talk about are subsets, which here A is a subset of B. Here you can see an underline underneath the symbol, and in the proper subset there is not an underline. The difference is that the proper subset, set A, has less elements than set B, but the normal subset, it could be equal as well. So if you want to write A is a subset of A, you have to put an underline underneath the symbol as well. And here are the examples. It's pretty easy. So don't forget that a proper subset is different. It just has less element. A set cannot be a proper subset of itself. And not a subset is obvious. Set A has at least one element, at least one, that is not in set B, like 66 here in the example. Now, let's move on to the next part, which would be power sets. So we'll start with power sets. The first thing is 2 to the power of the cardinal of set A, which is the number of all subsets of A. Now, what is A inside 2 lines? This is the number of all elements in A. As you can see, this is 3, so 2 to the power of 3 would be 8, which is the number of all subsets of A. And a power set that we define with rho or P is a set of all subsets of A. Now here you can see that I wrote all the subsets of A one by one. We calculated above that it would be 8 of them. Don't forget to add the empty set and the set A itself. And I write all of these subsets inside 2 braces, which would be a power set. 2 sets are equal if they have the same exact elements. A complement, which we will actually need a lot in probability, so don't forget to learn it, is everything that is not in set A, basically. A relative complement, which again we use a lot. There are 2 ways to show it, right there. Also, the symmetric difference we use a lot in probability. So the relative complement, which we write with A minus B, or the backslash, is everything that is in set A but is not in set B, so A minus B. Here are 2 examples of set A 3, 9, 14, set B 1, 2, 3, A relative complement, B is 9 and 14. 9 and 14 are everything in A, but they are not in B. So as you can see here, 3, which is in A and in B, so it belongs to their intersection, would not be in the relative complement set. The symmetric difference, which is very interesting, are objects that belong to set A or set B, but not to both of them. So not to set A and set B. So you might remember and or from the previous slide, which were union and intersection. This is how we also can write delta or symmetric difference. This little triangle is called delta. You can write A or B, so A union B minus, which is but not to, and A intersection of B. So they belong to set A or B, but not to their intersection. You can see the examples here with set A and set B. Let's move on to the part about the elements. This is pretty easy now that you got a hang of sets. So here we have a set A. You can see that any object inside set A is an element of it. You write not an element of. If it's not an element of A, it's not inside of it. Don't forget that if you put braces around an element, it's not an element anymore, it's a subset. An ordered pair is a pair in parentheses, which we'll need here in the Cartesian product. Cartesian product is a set of all ordered paired A and B, where A, the first one, belongs to the first set. Here is A. And the second one in the ordered pair belongs to the second set. Here is B. Here you can see an example. I wrote set A and B. I wrote set B, 5 and 6. You can see that the first ones here first ones in the ordered pair belong to the set A, so A and B. And the second ones in ordered pair belong to set B, 5 and 6. So now that you understand, now that you see the example, you can understand that the A Cartesian product of B, you cannot change the places. Next one, we talk about cardinality, which we talked before in the previous slide, is the number of all elements inside set A. Let's talk a little bit about Venn diagrams, which are a great fun way to visually represent sets and their relationships. Remember, these are not used for proving anything, rather just understanding the relationship. So I want to talk about the intersection and the union. First, as you can see, a Venn diagram initially is a universal set and two ovals or circles for sets. The intersection, of course, is the part that A and B intersect, or the things that are in both of them. What about the union? The union, of course, is pretty obvious. The union would be all of A and all of B. So if you want to color it, you would color all of A and all of B together. Obviously, as you can see, when we do this, we color the intersection part twice. Once when we color A and once when we color B. This is important later in counting and probability, because the intersection here is actually colored twice, and when we want to see the number of elements in A union B, we have to take the intersection part, we have to minus that at the end because we counted twice. What about A complement? What A complement is, we talked about it, is everything that is not in set A. Now, everything not in set A would or would not be in set B. It depends on the diagram itself. But at the end of the day, you look at the universal set that you have. Here is the rectangle, which we can actually show it with omega or with u. In the book, we use omega, I believe. This is why I used omega here. But in the previous slide, I used U for universal. This is the representation of a complement, which is everything that is not inside A. So basically, you color everything, but you decolor, I guess, if that's a word, A, set A. This is important because we use it a lot. We use actually Venn diagrams a lot in probability just to understand what the question is asking. Again, just to talk about it one more time, this is not proof. This is just a way to visually represent sets, which is a great way because it's easy. It's easy to understand. There you go. That's the Venn diagram. All right. Now that we have talked about Venn diagrams and you know what they are, how we draw them, and why we draw them, here are a few examples of very practical Venn diagrams with two sets, A and B. You can see the most important ones here, but the things I want to talk about is in this slide. It's very important to be able to understand a sentence and then write it mathematically in set theory and in probability, because we're gonna have to be able to understand it in probability, a sentence to mathematical form. Here we have three sets, A, B, and C. You can see set A is the Venn diagram. You can see not A in Venn diagram. You can see A and B, which is their intersection. We talked about it. A or B, which is the union. Again, we talked about it. These are also interesting. A or B or C, which is so the same thing with union, but 3. The next one is also interesting because you have two of the sets in parentheses. You have A or B and not C. So A or B would be A union B, and is the intersection, and not C is of course C complement. Next one is C and not A and not B. You may realize here it doesn't matter if we actually put two of the sets in parentheses if both or all of the elements between them is the same. So if all of them is intersection or all of them is union. Here you have the rest of it. You have the 4 a little harder ones. For example, the first one, A and B in parentheses, so A and B, or so we have union, and then A and C, so A and C in parentheses, again intersection. We also have or B and C, which I forgot to put here. I put it right here. Again, since between the parentheses all of them are union, it doesn't matter which parentheses come first. And we'll talk about the rules and the algebra in the next slide. Next one, again, since the first part we have B and C and not A, I put the first two ones as it's written in the sentence in parentheses, and then and not A goes in another parentheses. The next one, again, between all of them is and. These are great way to practice. Let's go to algebra of sets. This is very interesting. If you remember mathematical logic, I will write all of the symbols about mathematical logic that relate to this here. For example, we have P and P. If you remember, we have the argument P is equivalent to P. The same thing as A union A is A. The same goes with and intersection. Again, this would be easy once you draw the Venn diagram. It's obvious. Also, we have the argument P and false or 0. I wrote it doesn't matter. So the value of false would be 0. That's what I wrote here. With the intersection with false would be equivalent to false. Here you have A intersection, an empty set is an empty set. Look at the ones I mark here. These two are the identity elements of intersection and union, which means what we do to set A and intersection with this element. Right here, for example, for intersection, the element is the empty set. For union is, no, for intersection is the universal set. It means that they don't change, basically. That's what the identity element means. Here we have the commutative law, which means they can change places. P and Q, Q and P are equivalent, the same as A and B with intersection, B and A, they're equivalent. Same goes with union. Don't forget that it doesn't work with A minus B, and it doesn't work with the A cross B. You can draw a Venn diagram for the first one to see why not. Next is the associative law, which again, let's talk about, let's see the mathematical logic version. So you know that the argument P or Q or R, you can say that it's equivalent to the argument P or Q or R, because it doesn't matter where you put the parentheses, since all the ands and ors are the same. So it's both union or both intersection, so it doesn't matter. It works with delta, it doesn't work with negative relative complement and Cartesian product. The distributive law is essentially you take the first, so as you can see here, the element in inside the parentheses is different than what you see outside. So here, for example, outside is union, inside is outside, yes, outside is union and inside is intersection. So what you do is, as you can see, I draw it here, you have A union B, A union C, and the intersection goes in between two parentheses. The same goes with all the others that you can see here. This is interesting because if you try to memorize that and see that, not memorize, see the reason behind it, it goes backwards as well, like you factor a complement, no, you factor a intersection or a union. Next, we have the Morgan law, which you can see here. So not parentheses P or Q is the equivalent of not P and not Q. The same goes with complement. It affects A, it affects B, and it also affects what's in between. Look at how the A minus B and C works, because we have something that I am writing right here. So A intersection B complement is the same as A minus B. And you can draw the Venn diagram to see why, but this works. If A and B are two sets, A intersection B complement is the equivalent of A minus B, right? So this is why this kind of works like the Morgan law as well, because you have the complement here. And also don't forget that the as we have not P is the equivalent to P, not A or A complement is the same as A as well. Next, I have something interesting. So if A and B are two sets, you have these few very interesting, very cool things to know and remember, because we later can use them to prove different things. Here, actually, I have A minus B is A intersection B complement. I talked about it. The other ones are written. They are interesting. Let's choose one of them to actually prove. This is the one that I chose to prove. This is interesting because I'm going to prove with taking an element like x and say that it's in set A or in set B or A complement or B complement, anything. This is actually a way of proving something is an element, no, and a set is a subset of another set. This is a type of proof that we use taking an element. So we take an element to prove this here. So as you can see, this is if and only if. I will prove one side. So I will prove, suppose A is an subset of B. You have to prove you have to try to prove that B complement is a subset of A complement. So the method I used, I talked about it. You take an element X, you say that it's in B complement. So by definition of B complement, X could not be in B. That's why I wrote here. Next I have, so now we have X is not an element of A. Why? Because if X does exist in A, then it means that X exists in B because A is the subset of B. So everything inside A should be in B. But that doesn't work because in above we say A is not a part of B. So the counterpositive of the above sentence is that if X is not in B, then X is not in A, right? Next we have, so now that it's not in A, X is in A complement. So by definition of A complement, we have X is in A complement. It was not in A, so it's in A complement. So we took an element in B complement and we showed that it is in A complement as well. And that's why B complement is a subset of A complement. And that's the proof. So you can try to prove the other side as well. It's the same exactly. And that's how we prove this one. The other ones I talked about are pretty easy. The formula for delta is also important. Don't forget to know definitely and try to prove all of this just so you'll get used to it. All right, so now that you have a good understanding of set theory and everything that you need to know in order to be able to prove and solve questions, let's go ahead and solve two questions from chapter 1 from the book. The first one is question number 2. You gotta prove two different arguments. Now, these two are exactly the same if you change B and A with each other. So I'm gonna just prove one of them. A complement equals to the phrase that you can see here. Now, if you look closely, A complement and intersection is the same in both parentheses. This is the distribution law. If you don't remember it, go back and check it out. But if you do remember it, it would be pretty easy. There's nothing else you need to do here. So you basically factor, let's say, A complement and, or A complement intersection, and then B union B complement would be in parentheses, which is the universal set. So at the end it would be A complement intersection of the universal set, which is the A complement, because intersection of anything with the universal set is that set itself. Let's move on to the second one. Part B says show this thing. Now let's start by looking at the right hand side, since you can't really do anything with the left hand side. So the right hand side, if you look closely, we have 3 different parentheses. I'm gonna need you to look at the first 2, as you can see here. From these 3, look at the first 2. In the first 2, exactly the same thing as the previous question happens, where A complement intersection is the same. So we're going to take that out, A complement intersection, and then there would be a parentheses, B union B prime or B complement would be in parentheses, and that would give you A complement, exactly as we had in the previous example. Now you have A complement from the first part, and then there is union parentheses A and B complement. So what do we do with this part? So the union A and B complement, and the thing that we had from the two first parentheses, so we have to write them together, as you can see right here. I write them together, it would be A complement or parentheses A and B complement, which again, this is the distributive law. What you do is you add A complement or to both parties. It would be A complement or A and A complement or B complement. So A complement or A is the universal set, the intersection of that with the next parentheses, which is A complement or B complement. The intersection of anything with the universal set is that thing, so the parentheses would remain. And then with De Morgan law, you have A intersection B, all of that complement.